if we heat a carbonate, a metal carbonate, we're not going to balance them or anything. We're just going to say what we get. What do we get if we heat a metal carbonate, XCO3? Metal oxide plus carbon dioxide, CO2. Okay, so that's our first type. Number two, we have a metal bicarbonate, HCO3. Okay, and what do we get? Next door? Oh, sorry, I've got tutorial today. Sorry. No worries. Yes. Plus carbon dioxide and water. Okay, excellent. And the third one we learned was a metal chlorate. And what did we get? Metal chloride and oxygen. Okay, excellent. I don't think they're going to give you any that are too difficult to balance, so that's pretty much it. All right, so today we are looking at on page 49, we are looking at the reaction of an acid with a carbonate and with a bicarbonate. So if we have, it's basically a neutralization reaction, okay? But you can just treat it like a double replacement, all right? So start by treating it as a double replacement. The H is going to get together with the CO3, and the Ca is going to get together with the Cl, all right? Now, if we were to just do that, we would end up with CaCl2 plus, and then we would have the H and the CO3, so it would be H2CO3, yeah? But if H2CO3 is sort of left on its own, it will break down into water and carbon dioxide, okay? So if it's left on its own, that's what we get. So the H2CO3 breaks down into H2O plus CO2. Similarly, if we have our acid in a bicarbonate, we again, it's like a double replacement. So the H goes together with the HCO3. And the Na goes together with the Cl. So we end up with NaCl, which is pretty straightforward. And then we have an H plus, HCO3 minus, so that's again going to be H2CO3. And what does H2CO3 do? Breaks down into carbon dioxide plus water. So there we are. La la la. Done. Easy, yes? Okay, so it's just that one extra step. If you want to see what happens in terms of the Lewis structures, here's water. Okay, and while we're here, we might as well review that geometry of the water, right? Because we've probably forgotten a lot of our geometry. What hybridization is the O? What's the hybridization? What do we mean by hybridization? It is sp3, because we have 4 electron domains, 2 lone pairs, and 2 bonding pairs. So it's sp3. The electron domain geometry what's the electron domain geometry of oxygen? It is tetrahedral, yeah. And the molecular geometry is bent. Yes. What is our bond angle? Whoa. Is it 90 degrees? Less than 109.5 degrees. Okay, because that's the tetrahedral bond angle, but the lone pairs are more repulsive than the bonding pairs. What is the carbon hybridization in the CO3 2-? sp2. All right, so we got sp2, and that means what is our molecular geometry around the C? Trigonal planar. And what is the bond angle? 120 degrees. Which of these three bonds in the carbonate is the strongest? Yes. Sorry. The double bond. It would be nice if it were so, wouldn't it? But it's not. Why not? Have a think on that. I'm going to just go close that door. Yeah. They're resonance structures, so there is no double bond per se. There's only 3 bonds, which are all bond order 1 1/3. Okay? None. All the same. We have resonance. And all the bond orders are 1 1/3. Okay. So back to here though, let's take a look at what's actually happening here. We have a water, which has a hydrogen and a hydroxide. And this hydrogen attaches to this lone pair on the oxygen. Okay, so we break this bond here, and we form a bond with those 2 electrons there. Okay, and so we end up with this new bond here, and we have OH all by itself. Yes? Okay. Not much here. It's just basically, the only thing is maybe we could do a net ionic equation. So if we look at this one, we combine our H with our CO3. And so we get H2CO3, which then becomes H2O and CO2, and our Ca with our Cl, which then becomes CaCl2. Now, if we do our complete ionic equation for that, do you guys remember complete ionic equations? Yeah, okay, so hydrochloric acid will split apart because it is an acid and it is aqueous. So we get 2H plus and 2Cl minus. Is this ringing bells? Good. And we have our solid, CaCO3. And then our calcium chloride is soluble. So we end up with Ca and 2Cl minus and the H2O and the CO2. And when we go to do our net ionic equation, you'll notice that we have our spectator ion Cl2. And so our net ionic equation is 2H plus CaCO3 gives Ca2 plus H2O and CO2. Is good? Okay. Same deal here. Nothing really exciting. The only thing I guess to remember is if you have an acid, this is what type of acid is acetic acid? Is it strong or is it weak? It is weak because the only strong acids are, so I brought no clean clothes. You guys remember those? And even if you don't remember what each of these are, you're like, that's not acetic acid, right? Because we've got H2, SO4, HI, HBr. We've got HNO3, HCl, and HClO3. So those are our strong acids. So that means that's a weak acid. What do weak acids do in solution? Do they break apart? Yeah, they break apart, but only a little bit. Most of it stays together. So when you do a net ionic equation, so weak mostly stays together. So when we do our complete ionic equation, the weak acid stays together because that represents the vast majority of the molecules. And if we add our solid, then we get our salt and our water and our carbon dioxide. Is good? Hi. Are you ready to write one of those quizzes? Perfect.
Wait, no, the retesting from last.
Oh, the retest thing from last time. I am read the tutorial this morning. So.
Is it something I can grab for you?
No, it's fine. Let's see. There we go. Sounds good. I'm not sure if you can do this on your own. I'd like to do it with you. Not today. We'll do it tomorrow. Cool. All right. La 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 la. And then there's some exercises. Formula equation, complete ionic, and net ionic. Okay. Just a nice little review there. We are going to watch a wee little video on vapor pressure and boiling. Filter 9. Oh. The hell was that?
Oh, okay.
Yeah, dropped an earring. Bang. It's all good. It's all good. tinyurl.com/429 BWSKD. All right. Perfect. Okay. Vapor pressure. Do you guys remember anything about vapor pressure? Little bit. What is vapor pressure? And you guys need to speak louder because I'm trying to hear you at the back and I'm like, yeah, that sounds good. But I really actually, to be honest with you, I have no idea what you're saying back there. You need to project your voice.
The sound of me clicking and clapping on the whiteboard is louder. Yeah.
So, yeah, so the gas molecules escape and they go into the air. But in order to measure a vapor pressure, what kind of container does it have to be in? Closed, okay? So, because otherwise the gas will just continue to escape and you won't reach an equilibrium vapor pressure where the amount evaporating is equal to the amount recondensing, okay? So we can sense the presence of many solids, liquids, and gas by their smell. In each case, we are smelling the gaseous form of the substance, even if we see that it is a solid or a liquid. Liquids and some solids are continuously vaporizing. Atoms or molecules in the liquid or solid are moving into the gas phase. Molecules will leave the liquid if they have enough energy. Some molecules will lose energy in collisions and return to the liquid. Ooh. Exciting, yes? Is this what you envisioned? Okay, close. Next. If the container is closed, the molecules cannot escape. An equilibrium is reached. Now, do you guys remember what we talked about equilibrium? Equilibrium is when one rate is equal to the reverse rate. Yeah? Okay. So, an equilibrium is reached when the rate of molecules leaving equals the rate of molecules returning to the liquid. The number of molecules in the gas phase, will that change? No, because for every new one that goes up, another one comes down, so the total number stays the same. And the pressure they exert is called the vapor pressure of the liquid, and it increases with increasing temperature. If the container is open, the gas escapes and the liquid disappears. This explains why clothes dry. The water in the clothes moves from the liquid phase into the gas phase, leaving the clothes ultimately dry. However, on days when the humidity is 100%, the clothes do not dry because as many water molecules condense from the gas phase back onto the clothes as evaporate from the clothes. That's why it's really hard to line dry things in Vancouver, especially in the winter. I tried because I'm like, I'm going to save electricity and I'm going to like put my clothes on like a little thing and whatever. It worked great in the summer. It did not work in the winter. Everything smelled musty and was gross. And like, I'm like, nope, back in the dryer you go. Vapor pressure also explains why ice slowly disappears. During winter, even when the temperature is below freezing, water molecules slowly leave the solid and enter the gas phase. What is that process called? Yes. Sublimation, yes. The process is slow because not many water molecules have enough energy to leave the solid at the low temperature. I have a, a defrosting freezer compartment in my fridge so it doesn't build up frost. And my ice cubes, I had ice cubes in there at the end of the summer, and then I haven't needed ice cubes since. And now the ice cubes are gone. Like they're literally just no longer there. They've been sitting there since, end of September or so, and they've just sublimed over time. Ooh, look what we have here. What kind of diagram is that? Sorry? It is a kinetic energy diagram, also called a Maxwell-Boltzmann diagram. So it's a kinetic energy distribution. So that's what we've been focusing on for the last few weeks. And the vapor pressure of a liquid or solid increases with increasing temperature. This is because at a higher temperature, more molecules have enough energy to leave. So at a higher temperature, you would have more molecules over here with a higher kinetic energy, and thus they would be able to leave the liquid phase. Is good? Okay. In order to escape a liquid, a molecule must have a minimum amount of energy. In this case, the energy shown by the green line. So the proportion of molecules that have enough energy to escape would be represented by the area under that curve. Does that make sense? Okay, so this area would be ones that could. This area, this whole area under here, would represent the percentage of molecules that cannot escape. Just going to grab that. Let's go here. Let's go here. Oh, look at this. There we go. So you can see here we have the blue molecules. Maybe we should, there it is. So at our lower temperature, that's the, and this is on page 55. That's the percent of low temperature molecules that can escape to the gas phase. Whereas the red area is the percent of molecules at high temp that can escape. Is good? Okay. So hopefully that diagram explains why at a higher temperature you get more gas molecules escaping. Yeah, okay. Good, 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 good. And then they show it here. There we go. Is good. Same thing. Next. Oh, we've completed the vapor pressure activity. Hooray! All right. There's our vapor pressure. Vapor pressure depends only upon temperature, but it also depends upon what else? The strength of the IMFs. And you guys remember this from the IMF unit? Yeah? Okay. So, higher temperature. Do we have a higher vapor pressure or a lower vapor pressure? Higher temperature. Higher vapor pressure. If we have stronger IMFs, do we have a higher vapor pressure or a lower vapor pressure? Lower vapor pressure. I'm not quite sure this lesson is worth it in that you've sort of done a lot this before, but anyway, there we go. You have no homework over spring break because you guys are not taking my class right now and you're still doing things. So yay, enjoy. Okay? Thank you guys for being here. Oh no, it's just one of these slippy ones and it just fell out. Yeah. Thank you. Thank you guys. Good to see you.